ईयर स्टूडेंट्स, अगर आप इन वीडियो लेक्चर्स का मैक्सिमम यूटिलाइजेशन करना चाहते हो तो आई थिंक आपको ये इंप्रूव सेशन डेफिनेटली फॉलो करना चाहिए और रिलीजियसली फॉलो करना चाहिए। इंप्रूव सेशन क्या है, इसका लिंक डिस्क्रिप्शन बॉक्स में है, तो जाओ उसको चेक करो। इसके अलावा अगर आप व्हाट्सएप ग्रुप ज्वाइन करना चाहते हो, और मुझे लगता है आपको करना भी चाहिए, तो आप क्या करो, हमारे वेबसाइट पे जाकर के अपने कॉन्टैक्ट डिटेल्स दे दो या फिर इस व्हाट्सएप नंबर पे जाकर के अपने कॉन्टैक्ट डिटेल्स दे दो, सो दैट हम आपको उसमें ऐड कर सके। चलो अब पढ़ना शुरू करते हैं।
Hi, welcome back. In this video we will pick up where we left off in the previous video. So this is the second part in the work power energy theory. So let's start. In this segment I'll start with this topic, and this is potential energy and FC relation, where FC stands for conservative force. So suppose I have a scalar function u, okay, and in xyz system, so by definition the conservative force field for which this potential energy is defined, it's given by f conservative is minus gradient of u. Okay, now this gradient is a like vector operator, and it takes a scalar input, okay, and gives like three outputs if I'm talking about x, y, z coordinate. Okay, so this del is del by del xi plus del by del yj plus del by del zk. Okay, now this del is very like similar to what we have in general formula, the differentiation. This is known as the partial differentiation, and I hope like you are familiar with this term, partial differentiation. So it just takes a scalar function, and suppose I'm differentiating with respect to x, so it will assume everything else constant except the variable x. Okay, so in gradient form this force will be minus this gradient of u, and this gradient is going to take the scalar function u, so it becomes f is equal to minus del u by del xi plus del u by del yj plus del u by del zk. Okay, now I'll explain it with an example. Assume u is 2x square y z. Okay, so if I'm going to differentiate u partially with respect to x, I'll assume everything else constant. This is basically saying how much my u is going to change if I'm going to change my x like a little bit. Okay, so that ratio is the partial differentiation. So like differentiating with respect to x, I'm going to assume y and z constant. So and this is just going to follow the basic rule of differentiation, and this del u by del x becomes 4x y z. Similarly, del u by del y is 2x square z, and del u by del z is 2x square y. Pause this video to let it sink in if you are like if you cannot follow like how I'm getting this partial differentiation. This is just following the basic rule of differentiation. Okay, or you can say the power rule of differentiation, x to the power n formula. Okay, so this fx from this function you should be able to see this is your fx, this is your fy, and this is your fz with like this negative sign. So fx is minus del u by del x, fy is minus del u by del y, fz is minus del u by del z. Okay, so this force as a vector form is going to be this thing with a negative I, this thing with a negative j, and this thing with a negative k. So this is the same formula, and I've written it in terms of I, j, and k. And now suppose we want to evaluate at point xyz, that is 2, 1, minus 1, and I'm just going to put the values of 2, 1, and like 2, 1, and minus 1, and get this function form. Okay, so this says my the value, the vector form of the force at 2, 1, minus 1 is 8i plus 8j minus 8k. Okay, let's move on to the next topic. Okay, let's talk about equilibrium. Now, suppose we have been given a function, and this function is a single variable function. Okay, so this is a scalar u potential energy function. It depends only on the value of the x coordinate. Okay, so this is a single dimension function, and it takes a curve like this, and it goes to from a, b, b, e, c, and f. So here I've made a simple table. This is like these are my points a, b, c, d, e, f, and these are the values with the proper sign of just a sign of du by dx, the rate of change of potential energy with respect to x. And here I've written the force direction, and here's the equilibrium state. I'll explain one by one. So at point A, you should be able to see the slope of the curve is 0. So du by dx is 0, and since we have that formula f is equal to minus del u by del x I minus del u by del y j and minus del u by del z k. This is the vector function, and since it's only like dependent on x, so this term and this term goes to 0. I'm just dealing with some differentiation in the x function. Okay, so this f is just going to have a x component. Okay, so f is like in fy is going to be 0, f in fz direction is going to be 0. So at point a the slope of the curve is 0, so you cannot define the force directions. Is going to be na, so na stands for not applicable. And you should be able to see this is a state where the potential energy is locally like having the minimum value, so it's going to be a stable equilibrium state. Okay, and let's talk about point b. At point b and again at point c, the slope of the function goes to 0, so this du by dx term goes to 0. And again these points, like there is no force defined, so the direction is going to be not applicable. And again at b, the locally the function is going to have a maximum value, so it's going to be unstable equilibrium. And at c again it's going to be having a locally minimum value, it's going to be a stable equilibrium. Now let's talk about the other 3 points. So we have this point D and point E and point F. Okay, so at D you should be able to see the slope is positive, so du by dx is positive. And if du by dx is positive, your fx is negative of that. Okay, so this fx will be negative. So at D, du by dx positive and force is going to be in the negative I direction. And again this is like neither a stable or nor a unstable equilibrium state, so this is like a not applicable equilibrium state. Okay, now at point E your slope is negative, or your du by dx is negative, and that force, that negative of negative, it becomes positive, so the force is going to be in positive x direction. And again this is not a equilibrium state, so we are going to call it Na. And again at F, du by dx goes to 0, so there is no direction for force defined, so there is no direction of force, and the equilibrium state is going to be neutral equilibrium. So if your F is 0 and du by dx is 0 such that your u is not changing at all, so it's a flat line, in that case then the equilibrium state is going to be a neutral equilibrium state. Okay, so let's move on to the next topic. Okay, now suppose you have to calculate the potential energy of a given system in these kind of force fields. So one can be like gravitational force field, other can be a spring force, and the third one can be a electrostatic force field. All these forces are conservative in nature, that means work done by these guys in a loop is going to be 0. So in general I have the general formula, Fc is equal to minus du by dr, that is basically coming from F is equal to minus gradient of u. So if R like if u is a single dimension function, I can just like replace that gradient or that partial differentiation thing with minus du by dr, where r can be either x, y, z or anything like that. Okay, so in this case I can write minus fc dot dr is equal to du, and I'll take the integration both side, and this is going to be negative of work conservative, and this will be du integration is going to be delta u, or something like ui to uf. So this is uf minus ui, or I can also write work conservative is minus of delta u. So I'll take the simplest case. Suppose this is my PE, g is equal to 0, so at this level my gravitational potential is 0, or you can say u is equal to 0. If I'm going to move a body from point A to point B above the surface, and in second case I'm going to move the body from point A to point C, that is going to be below the surface. So think about this guy, this surface as table, and I'm moving a body up the table in one case and then down the table in the other case. So going from A to B, work done by the that conservative force, that is basically gravitational force, that is going to be negative because I'm going up and the force is acting downward, so that work done is going to be negative. Suppose this height is h and this height is also h, so this work conservative is going to be minus mg h. Again, from going from A to C, I'm going down and force is also acting in the downward direction, and that cos 0 is going to be 1. So in this case work conservative is going to be mg h. Using this formula for A to B movement, this work conservative is minus mgh, and minus mgh is going to be minus of delta u, so minus of delta u is minus uf minus ui, and so this gives you uf, and this ui is going to be 0, so this gives you uf is equal to mgh. So going above the reference frame or reference line, my potential is going to be positive. If I'm going down, that means coming from A to C, work conservative is mgh, and this is going to be minus again uf, again ui is going to be 0, in this case uf is going to be minus mgh. So coming down that surface, my potential is going to be negative. Going above, the potential is going to be positive. Okay, let's now talk about the potential energy in a spring body system. So we have a spring constant k and mass m attached to it, and somewhere here is my x is equal to 0 line, and this is my point A and this is my point B. So at point A, the spring is having like elongation of x1, and at point B the spring is having elongation of x2. So I'm going from point A to point B. Okay, so work done by spring, again it's a conservative force field, so work done by spring is going to minus of delta u, and that modulus is k into x, where x is the deformation in the spring at any general time t. Okay, so fs mod is going to be kx, work done by the spring going from point A to point B. If I'm going from point A to point B, my displacement is in this direction, right hand side, and my force is going to be towards left, and that angle is going to be 180 degrees, so there's going to be a negative work done. So I'm just going to write dw is equal to kxt x with a negative sign, because cos 180 is going to be minus 1, and again going from point x1 to x2, so my x goes from x1 to x2, and this integrates to k by 2 x1 square minus x2 square. Now from the formula we have work spring is equal to minus of delta u, and this minus of delta u is nothing but ui minus uf. So I can relate this equation with this equation, and ui minus uf goes to k by 2 x1 square minus x2 square. So this is the initial position and this is the final position. So you can again get the ui is going to be k by 2 x1 square, and uf is going to be k by 2 x2 square. So the general formula is going to look like k by 2 x square, or half k x square. So this is the potential energy function of a spring. Okay, let's move on to the electrostatic potential energy. So we have this electrostatic potential energy. The definition of electrostatic potential is given by k q1 q2 by r. So this is basically coming from potential energy of two charge particle kept at a distance r from each other, and the function can be rearranged in k q1 by r into q2, and then again this k q1 by r is defined as the potential. Okay, so we'll derive this formula in the later section of this crash course series. For the time it will be sufficient to know that this potential energy is like proportional to the product of the charges and inversely proportional to the distance between them. Okay, so this u can be written as this thing into q2, and this whole thing k q1 by r is defined as a potential due to charge q1. So this is v1, potential due to charge 1 into q2, or v2, I can like write this whole thing as k q2 by r into q1. So this is going to be v2 into q1. So this is like in general I can write the potential energy of like a single particle is like more like defined as two particle system but in many cases you're just going to be given a value charge q, and it is going to be in a given potential v. So you're going to write potential energy of that charge in that potential, or is coming from some electric field. In that case, that potential energy is q into v, where v is the external potential and q is the charge for which you're calculating the potential energy. Okay, now let's move on to the next topic, or this is going to be the final topic of this video, and this is going to be work energy theorem. Now these topics, problem involving chain and law of conservation of energy, we are going to discuss shortly in the next video. Okay, so let's start this work energy theorem. Work energy theorem is nothing but saying the total work done on a system by all the forces is going to be change in kinetic energy. So suppose on a body we have some forces Fc, that is going to be F conservative, and some forces Nc, some non-conservative force field, some F internal force, and let's give some name F external, some external force field. So net force is going to be Fnc plus Fc plus F internal plus F external. Okay, and we have that F net dot ds is basically your work done by the all these forces. So this is going to be W net. Okay, now this integration is W net, and we have F net is equal to M into A. Okay, and this is nothing but M, like we have this formula A ds is equal to V dV. So this integration is M A ds, and then again ADS is going to be V dV. So M V dV integration, that is going to be your work net. I can take M outside, and V dV going from some V1 to V2 is going to be V square by 2, like going from V1 to V2. So this is going to be M V square by 2 minus M V1 square by 2, and that is your work net. So it's saying work net work done by all the forces, basically changing kinetic energy of the body.